Okay, I'm going to get some more lectures for you on the Biot Savart law and do a little bit on it and a couple little examples. All I got's black today, so I'm at the barn, so I'm going to do what I can with here. We had an example 5.5. What I'm going to look at, example 5.5. And basically what it says, find the magnetic field a distance S from a long straight wire carrying a steady current. And so basically if you draw this out, basically you have a wire here. So you got a current going that way. And here's some point of interest. We'll call that point P. And we're going to look over some wire element right here. We'll call this some DL vector. And from where that's at up to the point of interest, we're going to give that our little script R, little cursive R. We're going to call that angle alpha. From a perpendicular point to the wire, we're going to call this S from it, and we're going to call this distance here L prime. So we're going to look at this element here for the wire, DL, and we're going to sum up a bunch of those and see how those affect the magnetic field there at point P. And this is the magnetic field caused by that long straight wire. Let me make sure it's working. Yep. Okay. So Biot-Savart law. If you remember Biot-Savart basically says that the B field as a function of distance from that wire is going to be equal to mu naught I. And I'm pulling the I out. This is the magnitude, and this is the I vector, with I as the magnitude and DL as the direction of that current, over 4 pi integral DL prime vector. Cross that with the vector from the point we're at, that script R, the point we're at where that DL is, to the point of interest. We're going to cross it with it. And we're going to divide that by the magnitude, basically that distance squared. Okay. All right. And if we look at this, well, it's going to go out of the page, right-hand rule. So it'll be out of the page. So the direction of B is out of the page. Okay. And we can do it with alpha here. Let's do it inside this triangle. If we go inside the triangle, if that's alpha, let's do that, make this theta. If we call that angle theta there. And basically when alpha is 180, theta would be 0. So that's the relationship between theta and alpha. So is alpha would be 90. My apologies. So when alpha is 90, when it's right here, alpha would be 90 degrees, theta would be 0. So they're basically complements of each other. Remember, complements, you add them together, equal 90 degrees. All right. And so if that's true, then DL, we'll say DL sine of alpha would equal L prime. I'm sorry, that's that distance there. DL sine of alpha, it would equal DL prime cosine of theta. And that's because they're complements of each other. Sine of 30 degrees is the same as the cosine of 60 degrees. Okay. All right. So now, what is L prime? We're basically doing this because we're going to substitute back into that here in a few minutes. So L prime, we know L prime, we know this, so that would be a tangent function. So we can say, we could write it as the tangent of theta equals L prime over S, or the L prime equals S tangent of theta. Okay, makes sense. Okay. And in DL here, let's look at DL. If that's true, then so that's what L prime is, tangent of theta. That means we solve this for DL. Excuse me. So what we can say is that DLS tangent of theta. Give me just a second here to get the geometry right. Okay, the book has, then we have that DL prime equals S over cosine squared theta d theta. Okay, now where did that come from? Let's see if we can figure out where that came from. Now, we have that theta's here. The tangent of theta, it's L over this. What would be the cosine of theta? Well, the cosine of theta would be S over that script R. We have here that DL sine theta equals, these two are equal to each other. But let's look at S. What's S equal to? S, let's look at that cosine of theta. Cosine of theta equals S over that script R. So S equals that script R cosine of theta. That's what S is. Okay. So now we've got this here, this here. But look, what we can do is bring S to the other side. So we can substitute, well, we want to keep that S. We want to keep that S. Okay. Now, tangent of theta is equal to what? Of course, that's sine theta over cosine theta. All right. All right. And so the book says this. Then the book says that we could write cosine squared theta. So cosine theta, we say is S over R, so cosine squared theta will equal S squared over that little script R squared. Or we can say, if we wanted to make it similar to this, we can make this equal to this to the other side, that 1 over script R squared equals cosine squared theta over S squared. And that will go in right in there. That's what we're doing that for. Okay. So this one we're going to use. We got DL go in right there. Okay. All right. So we're going to use this for DL. And if we do that, the B field, we go underneath the B field, we're going to get mu naught I over 4 pi. And we're basically going to take this angle theta and go from some angle to another angle. And that will sweep out some length on there. An integral with some theta 1 to some theta 2. And 1 over R squared is this, so we're going to take 1 over this part. That's going to be cosine squared theta over S squared. All right. DL is going to be here. And we know DL is S cosine squared theta. And this R there, we know R is equal. We put this over here. crossing it with R. So dl, and they get cosine theta d theta. Okay. And they get this from what they did was this right here is equal to this what I didn't show earlier. This term here, when I wrote it down, I read this wrong. This is dl cross r vector. That's what that is. So this is dl. So we found the dl prime that we're going to stick in right here. This we stick in right there. And rather than using for this dl, what we're going to do, we're going to do this one here. So we could stick it in on either side of that. So that's where this cosine theta comes from. And then we're going to take this and evaluate it between all the thetas from theta 1 to theta 2 that would be inscribed as we go down that length. So that's where it came from. My apologies for not seeing that earlier. It's my bad. Okay, so the cosine theta comes from right there, and then the d theta integral is all those angles. Okay, we can mark some stuff out here. That cancels. One of those cancels. And s is constant, so we can say this is really mu I over 4 pi s. Mu naught I over 4 pi s integral theta 1 to theta 2 cosine of theta d theta. What's interesting, a lot of these integrals, once you do the substitution right, it gets easy. Now, I will tell you, when this was first derived, they had to do a lot of work to know to do it in this way. I mean, people just didn't figure this out ahead of, just like that with it. There's a lot of mistakes made before you get here, trust me. And if we do that, well, we know what that integral is. That's just sine theta. So this is mu naught I over 4 pi s sine theta 2 minus sine theta 1. Okay. And this is within basically here to say there, or from here to here. You know, if this is theta 1 and that's theta 2, some angle gets inscribed there. Now, here's the deal. You haven't seen this before when we did it. If we do an infinitely long wire, then theta 2, which we'll say theta 2 is way over on the left-hand side, that would become an angle basically of, we'll call that negative pi over 2. The angle there is 90 degrees, assuming this is 0. That's negative pi over 2. That's pi over 2. And what is the sine of negative pi over 2? What's the sine of negative pi over 2? Well, the sine of negative pi over 2 is equal to negative 1. Negative pi over 2. So the sine of that is equal to, so if we go in here, that's going to be negative 1. Or 1, because it's 1 this way. And the sine of pi over 2, going the other way, is going to be negative 1. It's going to end up getting 2. Well, that 2 will cancel that 4. So for an infinitely long wire, something you've seen before, mu naught I over 2 pi s is the B field. You might have seen that as R if you remember from when we did 212. But it works out the same. Works out the same. All right, so questions there. Hearing none, I don't see the dogs. Don't see the cats. I see the dog. Hey, Lily. Well, she's sleeping. Let's look at example 5.6, and let me wipe the board off for that. And this one wipes off better than the one at school, doesn't it? All right. Look good, actually. Let's look at example 5.6. And here, you have to find the magnetic field at distance z above the center of a circular loop of radius r that's got a steady current. Again, these are steady currents. All right. So let's make a loop here. And up here, there's some point. Let's say right up here. And this is going to be your dl. That's the direction of that current. Of course, there's a current going in this. This is going to be the center. The distance up to that center, we're going to call that z. From this current point right here up to that point of interest, we're going to call that our little script r. And if this is our radius, call that our radius capital R. And that right there is our angle theta. And so at this point up here, we want to know what's the B field. Well, right-hand rule, the B field is going to be up like this. That's the direction of that B field. And what we want to do is we want to see what we got. See what we got going on. All right, so let's look at Biot Savart law. And that's the B field. Goes mu naught I over 2 pi. Excuse me, 4 pi. Go back. Over 4 pi integral dl, and that's just the differential length vector for that current. Cross that with our script r, basically where our current element is up to the point of interest, that vector, and divide that by that distance squared, because it falls off as 1 over the radius squared type system. Okay. So, of course, the solution says a differential, they do a dB is shown, integrate the current around the loop. It sweeps out kind of a cone, but as it sweeps out that cone, really only the component, because this will go here. And the next one will go there, but what happens is, one from the other side would have a B like this. If you remember from 212, hopefully you do, I doubt you do, but look it up if you want. That, of course, the two perpendicular components to Z, they'll cancel out because it's a circle. So they all get canceled out by the 180 degrees from it. So the only component that's left is the one straight up. So what you can do is, of course, it says the horizontal cancels, the vertical components combined. So really, it's just the cosine of theta of this that really matters, the cosine of it. And I have messed up. I am so sorry. That is the unit vector for it. That was probably some of my reasons I had issues in the previous one. So if it's the unit vector, we cross this and we only care about the cosine of it. That when we cross it, the magnitude is 1. So it's just going to be equal to mu naught I over 4 pi integral dl prime cosine of theta over r squared, that script r squared. So when we do that cross product, of course, you cross it and it crosses sine, but we only care about that cosine. The cosine component is the only one we care about here. All right. So if we look at this, how can we substitute? Well, cosine of theta is actually a constant because it stays constant as we go around. That's actually a constant as well. Because we go around that circle, that script r, that distance there between that current element and that point, they're the same distance all the way you go around. And who's going to do that? But I can't even do it. Maybe I need something to help me to do this, but it's kind of hard. It's help me to do that. It stays constant. So that's a constant. So those I can pull out. So really my integral And I'm really integrating around the circle. I'm going to integrate all these differential elements, length elements around that circle. Well, if you integrate around the circle, what is that? What's the diameter? It's the circumference of a circle. Just saw a bee flying in. And the circumference of a circle we know is 2 pi times the radius. In this case, the radius is big R. So what we'll do is, that's going to be mu naught I over 4 pi cosine of theta script R squared times 2 pi times big R. Now, we normally don't write things in terms of that little r from here. We want to use it in terms we know. So if we would do it in terms of just z, and I'll say that's the magnet, in terms of z and r, and capital R, that radius, that's what we know initially. Well, what do we know? We know cosine theta is r over that script, the radius over that script r, adjacent over hypotenuse. Okay, so this will be cosine theta is adjacent over this. But what is this thing here? Because now I'm left with 1 over r squared. That's really equal to, well, actually I'll put the 2 pi r up here. But that's just by Pythagorean theorem, z squared plus capital R squared. So I'm going to get rid of this. Just put z squared plus r squared. Now in this case, it's the square root because, well, nope, it's squared. I'm sorry. So, oh, it is only one of these. I'm sorry, that was right. It's the square root of z squared plus r squared. I know what the answer is supposed to be, so I know what's going to have to be. This one would go here, z squared plus r squared. So if I combine this, those cancel, leave me a 2 mu naught I capital R squared over 2. Now this is to the 1/2 power, and that's to the 1 power. Remember, a square root's always to the 1/2. Multiplying bases add exponents. The bases are the same, so 1/2 plus 1 is z squared plus r squared to the 3/2, or 1.5 power. And this is in your 212 book as well. So this is the magnitude of the B field at a point, a certain distance, a z distance away from a current loop in the center. If you're r off center, you got to take into account, when you do that integral around, it's a little bit more difficult. It's doable, but then you basically, at this point, depending on where it's at, these off-axis terms don't cancel, and you got to include those. Okay. And I think that will suffice for Biot Savart. Next, I want to look at the divergence and curl of B.